Okay, so welcome to Unit 4. The focus on this unit is going to be on exponential functions. Now we saw a little bit of these back in Unit 1. We were looking at some of the different parent functions. We looked a little bit at 2 to the x as an example of an exponential function. We'll look at a lot more of them coming up. But just to start off, we're just going to look at the whole idea between a function being increasing or decreasing, or in some cases neither. So let's just start with some examples of functions we've seen before. So the first two we have here, y equals 3x plus 7 and negative 5 bracket x minus 6 minus 2. These are examples of lines. So just to remind ourselves what these look like. So let's take a look at Desmos here. So y equals 3x plus 7, if you remember correctly, it should be a line with a y-intercept of 7 and a slope of 3. So it has a positive slope, and we are going to say that this line is increasing. So to define a function as increasing, you're looking at going from left to right on the graph, what's happening to the equation, or what's happening to the graph. So as we move left to right over here, the function is going up, so we say it is increasing. If you look at our second one here, the negative 5 bracket x minus 6 minus 2, this line has a negative slope, the slope of negative 5. So from left to right, again, our function is going down or decreasing. So this is a decreasing function. Okay, so going back, now let's try and take a look at some exponential functions. So y equals 2 to the x is a parent function that we saw back in Unit 1. So remind yourself what it looks like. Okay, so this would be considered an increasing function. So again, from left to right, the graph is going up. Some features a graph like this has a horizontal asymptote at y equals 0. So you can see if we zoom in, the graph gets infinitely close to 0 but never actually touches it or crosses it. So there's an asymptote there at y equals 0. So we can see here that 2 to the x is an increasing function from left to right. However, if you look at 0.5 to the x, this is actually a different parent function, similar shape to 2 to the x, but a different parent function. This one's actually going to be decreasing as you go from left to right. So you might think, well, why is this one decreasing while the other one's increasing? Well, you can look at some tables of values, but you can sort of see how as x increases, you're getting a higher power of 2 every single time. So it's going to keep growing faster and faster and faster. It's one of the reasons it's called exponential. This is called exponential growth 2 to the x. If you look at 0.5 to the x, you see it's as x goes up, it's a higher exponent on 0.5, which gets smaller and smaller. So this will be what we call an example of exponential decay. Okay, so in general, if you want to look at an exponential function, so y equals a to the x, so here the base is just a, you'll see that anytime our a value is larger than 1, we have an increasing function, so it's increasing from left to right. Once we get into being smaller than 1, okay, so anything between 0 and 1 here, and now we have a decreasing graph. Okay, so if you're looking at whether or not the parent function is going to be increasing or decreasing, you have to look only at the base. The base will tell you. Now, in the case of the base happens to be 1, you'll see 1 to the x. Well, any 1 to the power of anything is 1, so that would mean you have a horizontal line. This would actually be neither increasing or decreasing. But in terms of an exponential function, if the base is larger than 1, it's increasing. If the base is less than 1, but greater than 0, we are decreasing. Okay, you'll never have a base that is less than 0. Okay, with that in mind, let's take a look at this last example right here. So y equals negative 8 times 2 to the x. Now, if you first look at 2 to the x here, well, based on that, you'd think it is increasing. However, if you look in front here, we have a reflection. So this negative 8, the 8 gives you a vertical stretch of factor 8, but the negative gives you a reflection in the x-axis. So if you take an increasing graph, such as y equals 2 to the x, and you reflect it in the x-axis, you can probably picture the shape it's going to have. So picture this being reflected down, and its general shape will look something like this. Okay, so even though the parent function here is increasing 2 to the x, after that reflection across the x-axis, you can see we're now actually decreasing, because as we move from left to right on the graph is going down. Okay, with that in mind, so here's an example. Now, using Desmos or a graphing calculator, whatever you have in front of you, I'm going to give you a sketch of y equals 2 to the x plus 5, or you can do one yourself on your computer. And once you've seen the sketch, I want you to try and fill in all this information from the chart down here. So again, over here, I'll give you the sketch. So let's do 2 to the x plus 5. Let's make it a little bit thicker, easier to see. Zoom out a bit. So here's a graph of y equals 2 to the x plus 5. So now I'd like you to, using this graph, try and fill in the chart on this page. So once you're finished, come back and we'll take a look at the answers. Okay, so first things first, To get our parent function, best thing to do is just look at the base of what we have in our power here. So the base is 2, so our parent function is going to be 2 to the x. Okay, in terms of our mapping rule, remind yourself of how mapping rules work. Okay, for the x part of the mapping rule, you're going to look at what's changing in our variable here. So nothing's changing. It says 2 to the x here. It's still 2 to the x here. So nothing's changing for x. Outside the function, we're multiplying by 1, which doesn't change anything, but we add 5 here. So our mapping rule is just x, y plus 5. For horizontal asymptote, you can probably see it on the graph here. If I had to plot y equals 5, you can see that that's the invisible line there. A function gets really, really close to and never actually touches. Okay, so you may notice where that 5 can be found in the equation. It's the value of the vertical shift here, which kind of makes sense, right? On the original function y equals 2 to the x, our asymptote's at y equals 0. So that's been shifted up 5 from your mapping rule. Well, that makes sense. The asymptote would move up 5 as well. So very fast way to get the equation of the horizontal asymptote is just look at the vertical shift. Okay, so over here we get a horizontal asymptote at y equals 5. We have a domain of all real numbers. This will be true for every exponential unless there's a real life restriction on the problem. Okay, if you look at our range, again from the graph here, you can see that any y value larger than 5 is possible. Okay, we will not say y can be equal to 5 because again it never actually touches the asymptote. Okay, so our range will be y is greater than 5. Okay, you can see from the graph that this graph has no x-intercept and it has a y-intercept of 6. Okay, now you can always find the y-intercept just like you can for any other equation by replacing x equals 0 into the equation. So you can always calculate it, so we can do that here. So if we had the y-intercept, we put x equals 0, so you have y equals 2 to the exponent 0 plus 5. Okay, if you run that through your calculator, you'll see that 2 to the exponent 0 is 1. We'll talk about y in a later lesson. But you wind up getting 6 for your y-intercept. Okay, and you can see from the equation as well that we are actually going to be increasing from left to right. Okay, so again, our parent function 2 to the x is increasing. Hasn't been reflected at all, so it's going to stay increasing. Okay, so I'm going to give you guys another one to try now. So this is going to be negative 3 times 0.7 to the x plus 2. Okay, so we got negative 3, 0.7 to the x plus 2. Oops. Okay, so there's your graph, and again, try and fill in the chart with everything you know, and we'll take up the answers when you're ready. Okay, so for our parent function here, our base here is 0.7, so our parent function is 0.7 to the x, so that parent function is decreasing. Okay, we'll see. We can see from the actual graph here that it's increasing, but that's because of reflections. We'll talk about that later. So our mapping rule here, what's happening to the x? Well, it's x plus 2. Remember in the mapping rule for x, it's the inverse, so instead of x plus 2, it'll be x minus 2. Okay, and outside the function, outside the parent function, we're multiplying by negative 3. Nothing's added or subtracted afterwards, so our mapping rule is just negative 3y. Okay, horizontal asymptote, again from before, look at our vertical shift, or from the graph you can see it's going to be at y equals 0. Our domain, just like for any other exponentials, is all real numbers. Our range, if you look at the graph here, is going to be anything less than 0. So y is less than 0. Okay, this one again has no x-intercept because there's an asymptote at 0 that we can't touch or cross. Okay, for the y-intercept, let's see if we can get it from the graph here. So it's negative 1.47 about. Again, we could also calculate that by putting in x equals 0 into the equation. So we could put in right here, negative 3 times 0.7, x equals 0, 0 plus 2 is 2. So if you do 0.7 squared, that's 0.49 times negative 3. That gives you the y-intercept of negative 1.47. Okay, and we can see from the graph that this is also increasing. So again, we could also get that without looking at the graph, by looking at our parent function here. So our parent function is 0.7 to the x. Okay, that's a decreasing exponential because the base is less than 1. And with our reflection here, we've reflected across the x-axis. It's gone from decreasing to increasing. All right. So what I'm going to have you guys do here, you have a table of values for y equals 2 to the x. I'd like you to put in different values for x. So just from 0 to 6, run them through this equation and see what your y values are. When you're finished, I want you to take the first, second, and third differences for each for this table and see what kind of patterns you might run into. Okay, I'll do the first one for you. When x is 0, you put 0 in for x, 2 to the exponent 0 is 1. Repeat that for all the other ones. Okay, well, I'll reveal the answers for you in a sec. Okay, let's take a look at these values now. Okay, so you'll notice a pattern here. Every y value is doubling, which makes sense because if we increase x by 1, we're increasing the power of x by 1. Now if you look at our first differences here, notice here that they are not constant, so which makes sense because we know it's not going to be linear. If you look at our second differences, they're still not constant. If you look at our third differences, again, still not constant. So this tells us it's not linear, it's not quadratic. I mean, if we could see, we could keep going. And if we did the fourth differences, we'd find the exact same thing, right? No constant differences to be found. However, if you might see, if you look at your original table here, you see a bit of a common ratio here because we're always doubling the y values. So if instead of doing your differences, if you were to divide successive terms here, so if you did 2 divided by 1, you'd get 2. If you did 4 divided by 2, you'd get 2. And so on and so forth. Okay, 16 divided by 8 is 2. You continue on forever. So instead of constant differences, what we do have is instead a constant ratio. Okay, so this constant ratio in this case is 2, and it happens to be exactly the same as the base of the exponent. Okay, so that's the pattern you're going to see in the tables of values for any kind of exponential function, a constant ratio where that ratio is equal to the base of the exponent, or the base of the power. Okay, so that does it for the investigation. Okay, so you've done the worksheet already. If you haven't completed the homework from that, please do so now. And when you're ready, you can move on to the rest. Okay, so if you are finished that, let's just summarize here. So we've already talked about a lot of this already. So if you're just looking at the parent function, y equals a to the x, we can say it increases anytime you have a base that is larger than 1, so it's called exponential growth. So an example of that would be 1.3 to the x. That's larger than 1, so it's going to increase growth from left to right. Okay, if we want an exponential that's decreasing, we'd be looking at a base that's between 0 and 1. Now again, we can't have a negative base with these. It wouldn't make any sense given the situation. So if you have a base between 0 and 1, it'll be a decreasing exponential, which will model decay. So 0.2 to the x would be an example of that. Okay, the other thing we also noticed when we're talking about the horizontal asymptote, so it's defined as a line, so let's just say we call it q, and that value q is going to be the vertical translation of the vertical shift. So to show you that over here on Desmos, okay, so here's, for example, y equals 2 to the x with a bunch of different parameters mixed in. You can see what happens as I change different values. We'll talk about the transformations in a sec, but you can see when I change this q value here, it changes the horizontal asymptote. Okay, that asymptote moves with the vertical shift. Okay, so if you want to look at some other transformations here, you can see the k, just like before, is a horizontal stretch compression. If it's negative, you'll see a reflection. Okay, horizontal reflection, reflection of the y-axis. For our p-value here in the equation change, that's going to be a horizontal shift. Okay, you can have our a value change, which again will be a vertical stretch or vertical compression. And if it's negative, we're going to see a reflection in the x-axis. Okay, but the big thing I want you to see here in terms of finding the asymptote is it is going to be equal to that q value right there, so that vertical shift. Okay, if we're looking at whether a function increases or decreases, now we've talked about how a parent function increases or decreases based on the base. If you want to find out if a transformed version increases or decreases, it'll depend on two things. So number one, it'll be based on your parent function. So you look at the base of your parent function. If it's larger than 1, it's going to increase. If it's between 0 and 1, it's going to decrease. But then you have to look at see if there's any reflection. So each reflection that you do, whether it's a reflection across the x-axis or reflection across the y-axis, will change whether the function is increasing or decreasing. So if you have one reflection, it will be the opposite behavior to the parent function. So for example, the parent function increases, you have one reflection, now your function is decreasing, okay, or vice versa. But if you have two reflections, so a reflection across the x and a reflection across the y, it'll be the same behavior as the parent function. So I'll quickly show you an example here. So here, if I make the a value negative, so this one's increasing right now. If I make the a value negative, I'm now decreasing. If I make k negative, get a reflection there, you see I'm increasing again. Okay, so every reflection that you do will change from increasing to decreasing, or vice versa. Okay, we're just going to finish this up in part 2, and we'll see you over there. Cheers.